Good day, everyone. Today we are opening a new discussion in logic circuits and design, Karnaugh Maps. You've already spent time building Boolean expressions from truth tables and simplifying them algebraically using the theorems of Boolean algebra. That approach works, but it has a serious weakness. As the number of variables grows, algebraic manipulation becomes tedious, error-prone, and extremely difficult to verify visually. The Karnaugh Map, named after Maurice Karnaugh, who introduced it at Bell Labs in 1953, solves this problem by rearranging the truth table into a two-dimensional grid where logical adjacency becomes visual adjacency. Patterns that would take many algebraic steps to simplify jump out immediately as rectangular groupings on the map. By the end of this discussion, you will be able to draw K-maps, read them fluently, and derive minimal sum of products and product of sums expressions with confidence. We will also cover the special case of don't care entries and close with a brief look at timing hazards, a real-world concern in combinational logic design. Let's get started. Let me walk you through what we are targeting today, 5 concrete, measurable objectives. Objective 1 is to construct K-maps. You need to be able to take any Boolean function expressed as a truth table, a minterm list, or a Boolean expression, and map it directly onto a 2, 3, 4, 5, or 6 variable Karnaugh map, without error. Objective 2 is to minimize SOP expressions. This means finding the prime implicants, identifying which ones are essential, and selecting the fewest groupings that cover every one cell. The result is a minimal sum of products. Objective 3 is the dual, minimizing POS expressions by grouping the zeros on the map instead of the ones. Objective 4 is handling don't care entries. Some minterms are physically impossible or irrelevant to the system. We mark them with D and use them opportunistically to enlarge our groups and reduce expression complexity further. Objective 5 is eliminating timing hazards, brief output glitches caused by unequal gate delays. K-maps give us a direct, visual method to detect and eliminate them. So what exactly is a Karnaugh map? At its core, it is a two-dimensional truth table. Every row of the truth table corresponds to exactly one cell on the K-map. But instead of listing inputs in natural binary order, 0, 0, 0, 1, 1, 0, 1, 1, the K-map arranges them so that adjacent cells differ in exactly one variable. This is called a gray code arrangement. Look at the two-variable example on the right. The truth table for A XOR B, Z equals A prime B plus AB prime, shows Z equals 1 for inputs 0, 1, and 10. When we place those values onto the 2 by 2 K-map, the two ones appear in positions row 0, column 1, and row 1, column 0, diagonally opposite. These cannot be grouped because they are not adjacent in the gray code sense. That tells you immediately that no further simplification beyond the two-term expression is possible. Now look at the second small map in the lower right. This shows the minterm numbering for a two-variable map. Cell 0 corresponds to minterm 0, cell 1 to minterm 2, cell 2 to minterm 1, and cell 3 to minterm 3. Notice the gray code ordering. This numbering becomes essential when you work from a minterm list. The core takeaway, simplifications that would require multiple steps of Boolean algebra appear as obvious rectangular groupings of ones on the K-map. This is not magic. It is the direct consequence of the gray code layout. Let's look at the actual structure of 2-variable and 3-variable maps in detail. For the 2-variable map on the left, you have a 2 by 2 grid. Row index is A, column index is B. I've plotted function where Z equals 1 at minterms 1 and 2, corresponding to A prime B and AB prime, which gives us Z equals AX or B. The two ones are diagonally placed and cannot be combined. So the minimal expression is exactly the two terms shown. Now for the 3-variable map. We have 8 minterms arranged in a 2 by 4 grid. The row is indexed by A and the columns by BC. Notice the column headers, 0, 0, 0, 1, 1, 1, 1, 0. This is a gray code sequence. Is not natural binary order because that would place BC equals 1, 0 and BC equals 1, 1 adjacent, but they differ in 2 bits, not 1. The gray code guarantees single-bit adjacency between every neighboring pair. On the right, you can see the alternate vertical form of the 3-variable map. Both forms are equivalent. The vertical form is used in some textbooks and is A across the top and BC down the side. At the bottom of this slide, I've summarized where each variable equals 1 in the 3-variable map. A equals 1 occupies the second row, B equals 1 occupies the 2 rightmost columns, BC equals 1, 0, and BC equals 1, 1. C equals 1 occupies the middle two columns. BC equals 0, 1, and BC equals 1, 1. Memorize these regions. They are the foundation for reading product terms from your groupings. One more thing, wrap around. The leftmost and rightmost columns are also adjacent because they differ in only one bit. BC equals 0, 0, and BC equals 1, 0 differ only in B. A grouping that spans the left and right edges is perfectly valid. Most exam mistakes come from forgetting this. Now we scale up to the 4-variable map, the most commonly encountered map in practice. We have 16 cells arranged in a 4 by 4 grid. The rows are indexed by AB and the columns by CD, both in gray code order, 0, 0, 0, 1, 1, 1, 1, 0. The full truth table for this example is shown on the right. 16 rows, one for each combination of A, B, C, D from 0000 to 1111 with Z values listed. Let me walk you through the minterm numbering. The cell at row AB equals 0, 0, column CD equals 0, 0 is minterm 0. The cell at row AB equals 0, 0, column CD equals 0, 1 is minterm 1. At AB equals 0, 0, CD equals 1, 1, we have minterm 3. At AB equals 0, 0, CD equals 1, 0, we have minterm 2, not 3, because of the gray code column ordering. This is a critical point. The column order swaps the positions of minterms 2 and 3, 6 and 7, 10 and 11, 14 and 15. Many students get their K-maps wrong by placing minterms in natural binary column order. Always write the column headers before you fill in values. Now look at the banner at the bottom. All 4 edges wrap around. The top row, AB equals 0, 0, and bottom row, AB equals 1, 0, are adjacent. They differ only in A. The leftmost column, CD equals 0, 0, and rightmost column, CD equals 1, 0, are adjacent. They differ only in C. This means corner cells minterms 0, 2, 8, 10 form a valid group of 4, and students almost always miss this. Take a moment to locate some minterms in the map at the center. M7 is at AB equals 0, 1, CD equals 1, 1. M13 is at AB equals 1, 1, CD equals 0, 1. M15 is at AB equals 1, 1, CD equals 1, 1. These will be important in the next 2 slides. This is the most important slide in the deck. Every K-map problem you will ever solve comes back to these 5 rules. Rule 1. Group size must be a power of 2. Valid sizes are 1, 2, 4, 8, or 16 for a 4-variable map. Groups of 3, 5, 6, or any other non-power of 2 are always invalid, as in always. Rule 2. Groups must be rectangles. This includes wraparound rectangles, a group that spans the left and right edges, the top and bottom edges, or even all 4 corners. But no L shapes, no T shapes, no diagonals. Only rectangles. Rule 3. Always maximize group size. A larger group eliminates more variables and gives a simpler term. You should always try to make your groups as large as possible, even if it means overlapping with other groups. Rule 4. Cover every one cell. A one cell that is not covered by at least one selected group means your expression is wrong. It will produce 0 for an input that should give 1. Rule 5. Minimize the number of groups. More groups means more terms, which means a more complex circuit. You want the fewest groups that still cover all one cells. On the right, I've summarized how to read the product term from a group. For each variable, if it equals 0 in all cells of a group, include the complemented form in the term. If it equals 1 in all cells, include the uncomplemented form. If it varies between 0 and 1 across the group, that variable is eliminated. That's the whole point of grouping. The 3 key terms at the bottom are essential vocabulary. A prime implicant is the largest possible valid group for a given set of 1 cells. An essential prime implicant is one that covers at least one cell that no other prime implicant covers. You have no choice but to include it. A distinguished one cell is any one cell covered by exactly one prime implicant. Find these first. They lock in your essential prime implicants immediately. Let's see the algebra behind what happens when we group 2 adjacent cells. The example is M5 plus M13. Minterm 5 is at AB equals 0, 1, CD equals 0, 1, corresponding to A prime B C prime D. Minterm 13 is at AB equals 1, 1, CD equals 0, 1, corresponding to A B C prime D. On the 4-variable map in the center, you can see these two cells highlighted in column CD equals 0, 1, rows AB equals 0, 1, and AB equals 1, 1. Now follow the algebra. When we expand the sum, A prime BC prime D plus ABC prime D, factor out B, C prime, and D, we get the quantity A prime plus A, multiplied by BC prime D. Since A prime plus A equals 1 by the complement law, the result is simply BC prime D. What happened? Variable A varied across the group. It was 0 in M5 and 1 in M13, so it was absorbed and eliminated. Variables B, C prime, and D were constant across both cells, so they remain in the product term. Below, you can see the equivalent logic circuits. Before grouping, you need 2 and gates feeding into 1 or gate, a total of 7 input connections. After grouping, a single 3 input and gate suffices. This is the direct hardware benefit of K-map minimization. The general principle, in a group of 2 raised to I cells, exactly I variables are absorbed, leaving a product term with K minus I literals for a K variable map. A 2-cell group absorbs 1 variable. A 4-cell group absorbs 2. An 8-cell group absorbs 3. Now let's extend this to a 4-cell merge, specifically M3 plus M7 plus M12 plus M13. Look at the 4-variable map in the lower left. Minterms 3, 7, 12, and 13 are highlighted. This is not a single rectangular block. Notice that 3 and 7 are in the left half of the map, while 12 and 13 are in the right half. However, they do form 2 separate valid groups of 2. Working through the algebra, the expansion gives A prime B prime CD plus A prime B CD plus ABC prime D prime plus ABC prime D. Factoring carefully, B prime plus B absorbs to 1, giving us A prime CD. And C prime D prime plus C prime D gives ABC prime. So the minimal SOP is A prime CD plus ABC prime. On the right, the K-map with the highlighted groupings confirms this. One loop captures M3 and M7 via A prime CD, and a second loop captures M12 and M13 via ABC prime. Now look at the table. A group of 2 eliminates 1 variable, leaving 3 literals. A group of 4 eliminates 2 variables, leaving 2 literals. A group of 8 eliminates 3 variables, leaving 1 literal. A group of 16, all cells, eliminates all 4 variables and collapses to the constant 1. This is the key quantitative insight. Every time you double the group size, you eliminate 1 additional variable. Always push for the largest group possible. This slide is your turn. The problem, given that Z equals the sum of minterms M5 plus M7 plus M13 plus M15, derive the minimal SOP expression. First, locate these minterms on the 4-variable map. Then, examine the map. Now read off the product term. You should get Z equals BD. For the algebraic derivation, try it yourself. You can pause this video while you solve for Z. Final answer should be Z equals BD. This is a clean result. 2 variables, 1 product term minimal. This slide is your visual reference for all valid grouping shapes in a 3-variable map. There are 6 canonical examples shown here, labeled Z1 through Z6. Z1 shows a horizontal pair, 2 adjacent cells, in the same row. This eliminates 1 variable. Z2 shows a vertical pair, 2 adjacent cells, in the same column. Again, 1 variable is eliminated. Z3 and Z4 show pairs that are vertically aligned but not in immediately adjacent rows. These are valid because the rows follow gray code order, so even non-consecutive looking rows may differ in only 1 variable. Pay attention to which rows are actually adjacent in the gray code sense. Z5 shows a vertical group of 4, a full column of 1s. This is a 4-cell group that eliminates 2 variables, leaving a single literal product term. Z6 shows a wraparound horizontal group, 2 cells at the far left and far right of the same row. Even though they appear separated visually, the leftmost column, BC equals 0, 0, and rightmost column, BC equals 1, 0, differ only in variable B. So these are adjacent, and this is a completely valid group. The wraparound examples are the ones students most frequently miss in exams. Train your eye to see the K-map as a torus. Both the left, right, and top-bottom edges connect seamlessly. Any rectangular arrangement that would be visible if you folded the map into a cylinder or a torus is valid. Here are the first 8 valid grouping shapes for the 4-variable map, Z7 through Z14. Z7 is a vertical pair, 2 adjacent cells in the same column. eliminates one variable, giving a 3 literal term. Z8 is a horizontal pair, 2 adjacent cells in a row. Z9 is a top-bottom wraparound pair, the same column position in the top row, AB equals 0, 0, and the bottom row, AB equals 1, 0. These differ only in variable A, making them adjacent. This trips up many students because the two cells appear to be far apart on the grid. Z10 is a left-right wraparound pair, same row, leftmost and rightmost columns, differing only in C. Z11 is a 2 by 2 square, a group of 4. Eliminates 2 variables, giving a 2 literal term. Z12 shows a vertically elongated 4-cell group, a group of 4 arranged in a single column. This covers all 4 rows of one column, which means both row variables, A and B, vary. Both are eliminated, leaving a 2-variable product term in C and D. Z13 is a horizontal 4-cell group, an entire row. Row is constant, so the 2 row variables are constant, but both column variables vary. C and D are eliminated, leaving a product term in A and B. Z14 is a left-right wraparound 4-cell group, 2 cells on the left edge and 2 cells on the right edge, same 2 rows. This forms a valid 2 by 2 rectangle when the map wraps. Notice that valid groups are always power of 2 rectangles. If you cannot see a rectangle, even accounting for wraparound, the grouping is invalid. Continuing with Z15 through Z20, these are the larger groups and the more exotic wraparound shapes. Z15 is a vertical group of 4 in a single column, all 4 rows. This is a group of 4 that eliminates 2 variables. Z16 is a horizontal group of 4 in a single row, an entire row. Eliminates 2 variables. Z17 is a 2 by 4 block, 8 cells filling half the map. Eliminates 3 variables, leaving a single literal product term. Z18 is an 8-cell group spanning 2 full rows. Also eliminates 3 variables. Z19 is a top-bottom wraparound 4-cell group, 2 cells in the top row and 2 in the bottom row at the same column positions. Even though they appear at opposite ends of the map, the top row, AB equals 0, 0, and bottom row, AB equals 1, 0, differ only in A. Z20 is a left-right wraparound group of 8 for cells in the leftmost column and 4 in the rightmost column. This is valid because those columns differ only in C. The extreme case is a group of all 16 cells, the entire map. This gives the constant function z equals 1. I want you to internalize that the valid shapes are not as restrictive as they might seem. Because of the torus-like adjacency structure of the K-map, many shapes that look disconnected on the flat grid are in fact rectangles when you account for wraparound. The test is always, do all cells in my proposed group form a rectangle, possibly with wraparound, and is the size a power of 2? Let me be very direct about what not to do. Look at the left side first, violates Rule 1. 3 cells are highlighted in the first column. The cells at AB equals 0, 0, AB equals 0, 1, and AB equals 1, 1. Someone grouped 3 cells. Rule 1 states that group size must be a power of 2. 3 is not a power of 2, is not 1, 2, 4, 8, or 16. This grouping is invalid, full stop. The fix is simple. Either expand to 4 cells if there are ones available to include, or shrink to 2 cells and handle the remaining cell with a separate group. Now the right side violates Rule 2. An L-shaped grouping, the top left 2 by 2 region minus the bottom right cell of that region. 3 cells form an L. Even though each cell individually is adjacent to at least one other, the L shape as a whole is not a rectangle. Rule 2 requires that all grouped cells form a rectangle. The algebraic reason, for a product term to emerge cleanly from a grouping, the grouping must cover exactly a hypercube subspace in the Boolean cube. Only rectangular groupings, including wraparound ones, correspond to valid hypercube subspaces. L shapes and T shapes do not. The fix here is to split the L shape into 2 valid groups of 2, one horizontal pair and one vertical pair, possibly overlapping. I want you to burn these 2 errors into memory because they appear on every examination. When in doubt, check, is my group size a power of 2? Is my group a rectangle? If either answer is no, the grouping is invalid. Up to now, we have been minimizing sum of products expressions, grouping the ones on the K-map. Now, we turn to the dual problem, minimizing product of sums expressions, which requires grouping the zeros. The duality is exact. Everything you know about SOP grouping applies to POS, The same 5 rules, the same rectangle requirement, the same power of to-size constraint. The only difference is what you are grouping and how you read the literal. Look at the comparison on this slide. For SP, group the ones. If variable x equals 0 in all cells of the group, you include x prime in the product term. If x equals 1 in all cells, you include x. If x varies, you eliminate it. For POS, group the zeros. The conventions are complemented. If x equals 0 in all cells of the 0 group, you include x, the uncomplemented literal, in the sum term. If x equals 1 in all cells, you include x prime. If x varies, you eliminate it. This distinction is the most common error I see in examinations. Students apply SOP literal rules when solving POS problems. The mnemonic I recommend: in POS, a constant 0 contributes the uncomplemented variable. Think of it this way: the 0 group is where the function is 0, and a variable that is also 0 throughout that region is asserting itself naturally, so it appears without complement. The decision rule at the bottom is your practical guide. Count the ones and the zeros on your map. If there are fewer zeros, POS is likely to give you fewer groups and a simpler circuit. If there are fewer ones, go with SOP. But always verify both. The counts are a heuristic, not a guarantee. Don't care entries are one of the most powerful tools in K-map minimization, and they arise constantly in real-world design. A don't care entry, denoted by the small letter d on the map, represents an input combination for which either the output can be anything or the input never occurs in practice. Examples include excess states in BCD arithmetic, where inputs 1010 through 1111 never appear, or fault detection logic, where certain sensor combinations are physically impossible. When a minterm is marked as don't care, it means you are free to treat it as either 0 or 1, whichever serves your minimization better. The strategy is, when you form groups of ones for SP, look at adjacent don't care cells and include them in your group if doing so makes the group larger. A larger group means fewer literals in the product term. Look at the 3-variable example on the right. We have z equals 1 at positions a equals 0, bc equals 1 1 and a equals 0, bc equals 1 0, and also at a equals 1, bc equals 0 0, and a equals 1, bc equals 0 1. The don't care sit at a equals 0, bc equals 0 1, and a equals 1, bc equals 1 1. If we treat the don't care at bc equals 0 1 as 1, we can extend a group to cover a equals 0, bc equals 0 1, bc equals 1 1, and bc equals 1 0, a group of 3. But wait, 3 is not a power of 2. We cannot do that directly. Instead, look at what groupings are possible. The ones at a equals 1, bc equals 0 0, and a equals 1, bc equals 0 1 can be grouped with the one at a equals 0, bc equals 0 0, treating the don't care at a equals 0, bc equals 0 1 as 1, giving a valid 2 by 2 block. The 3 rules include don't cares in your 1 groups if they allow a larger grouping. Never form a group consisting only of don't cares. You must include at least one actual one, and use don't cares default to 0 for SP, so they are simply ignored in the final expression. The classic application is BCD logic. All 6 states from 1010 to 1111 are don't cares. This often allows a 4-variable function that would otherwise require 4 product terms to be expressed with just 1 or 2. When the number of variables exceeds 4, the K-map structure changes from a single flat grid to a set of stacked submaps. For a 5-variable map, we use 2 side-by-side 4-variable K-maps. The left half represents a equals 0, and the right half represents a equals 1. Together, they contain 32 cells, 2 to the 5th power, 1 for each 5-variable minterm. The critical concept here is cross-submap adjacency. Cells at the same relative position in both submaps, same row, same column, are adjacent because they differ only in variable A. Look at the 2 maps. Cell at row CD equals 0 1, column AB equals 0 1 in the left half is M5. The corresponding cell in the right half is M21. These 2 cells differ only in A, so they are adjacent and can be grouped. A group that appears identically in both halves of the 5-variable map, same shape, same position, spans 2 times the size of that shape. So a valid 4-cell rectangle that appears in both halves yields an 8-cell group, eliminating 3 variables, with variable A also absorbed. The maximum group is 32 cells, all of both halves, giving the constant function z equals 1. There are two common visual formats for the 5-variable map, the side-by-side format shown on the left of this slide and the flat 4:8 format shown on the right. The flat format lays the two halves out sequentially. Both are equivalent. The flat format is sometimes easier to draw on paper. The side-by-side format makes cross-submap adjacency more intuitive. Practical advice: for 5 and 6 variable functions, K-map minimization is still feasible but becomes quite tedious. Beyond 6 variables, use algorithmic methods, the Quine-McCluskey tabular method, or software tools like Espresso or Synopsys Design Compiler. The 6-variable map extends the concept one step further. We now have 4 variable submaps arranged in a 2x2 grid. The 4 quadrants correspond to the 4 combinations of variables a and b. A equals 0, b equals 0 in the upper left, a equals 0, b equals 1 in the upper right, a equals 1, b equals 0 in the lower left, and a equals 1, b equals 1 in the lower right. Each quadrant contains 16 cells for a total of 64 cells, 2 to the 6th power. Cross-submap adjacency now works in 2 dimensions. Cells at the same relative position in horizontally adjacent submaps differ only in B. Cells at the same position in vertically adjacent submaps differ only in A. And cells at the same position in diagonally opposite submaps can also be grouped. They form a 4-cell group spread across all 4 quadrants, differing only in A and B. A group that occupies identical positions in all 4 quadrants is a group of 4 times the base rectangle size. If the base rectangle is a 4-cell group, spanning all 4 submaps gives a 16-cell group, eliminating A and B in addition to whatever variables the base rectangle eliminates. The maximum group for a 6-variable map is 64 cells, the entire map collapsing to constant 1. As with a 5-variable map, there is an alternate flat representation where the 4 submaps are unfolded into an 8x8 grid. Some textbooks prefer this format. The practical limit for K-map use is 6 variables. Beyond that, the visual benefit disappears and the method becomes error-prone. In industry and in advanced coursework on VLSI design, you will encounter algorithms like Espresso and synthesis tools that can minimize functions with hundreds of variables in milliseconds. But the K-map gives you the conceptual foundation those algorithms are built on. Even a perfectly minimized Boolean expression can produce incorrect output in a real physical circuit, briefly and transiently. These transient errors are called timing hazards, and the K-map provides a diagnostic tool to detect and eliminate them. Let's start with the static 1 hazard. The circuit output is supposed to stay constant at 1 as one input variable transitions from 0 to 1. But in a 2-level AND/OR network, you have multiple product terms, each realized as an AND gate, feeding into a final OR gate. When one input changes, one AND gate is turned off while another is turning on. If the turn-off happens slightly faster than the turn-on, due to different path delays, the output momentarily drops to 0 before recovering. This brief low pulse is the static 1 hazard. How do you detect it on a K-map? Look for any 2 adjacent 1 cells that are not both covered by a single common loop. If a variable transition would move the operating point from one of those cells to the other, and no single product term covers both, a hazard exists. The fix is to add a redundant product term. Draw an additional loop that covers both 1 cells. This term is logically redundant. It does not change the function, but it ensures that at least one AND gate remains asserted throughout the transition, preventing the glitch. For the static 0 hazard, the dual case in POS networks, the output should stay at 0, but briefly spikes to 1. The diagnosis is the same concept applied to 0 cells. The fix is a redundant sum term covering the adjacent 0 cells. An important qualification. In synchronous digital systems clocked by flip-flops, hazards only matter if they occur during the setup and hold window of the receiving flip-flop. If glitches are guaranteed to have settled before the clock edge, they cause no functional error. But in asynchronous logic and in the feedback paths of sequential circuits, hazard-free design is non-negotiable. The added redundant term does not change the Boolean expression or the truth table. It only changes the physical behavior of the circuit in time. This comparison table consolidates the complete duality between SOP and POS minimization. Both forms represent exactly the same Boolean function. The choice between them is purely a matter of circuit efficiency, which form produces fewer terms and fewer literals. The decision heuristic: count the 1s and 0s on your K-map. If there are fewer 0s than 1s, you will likely need fewer groups to cover all 0s, making POS simpler. If there are fewer ones, SOP is likely simpler. But this is only a heuristic. The actual group structures matter more than the raw counts, so always verify both forms when the counts are comparable. The most important row in this table is the literal convention for constant variables. For SOP, if x equals 0 throughout the group, include x prime. If x equals 1, include x. For POS, the conventions are swapped. If x equals 0 throughout, include x, the uncomplemented form, in the sum term. If x equals 1, include x prime. This distinction is where almost everyone makes their first POS error. Burn it in a POS 0 group, a variable that stays 0 appears without a complement. The prime term concept mirrors itself as well. A prime implicant is the maximal grouping of ones. A prime implicate is the maximal grouping of zeros. The selection procedure is identical. Find all prime terms, identify essential ones, cover the remaining uncovered cells with the minimum number of additional prime terms. For your examinations, when the problem asks for the minimal expression, check both SOP and POS report the one with fewer terms, or fewer total literals, if the term count is tied. Show your work on both maps. Let's close by consolidating the 6 most important ideas from this lecture. Point 1. The K-map is a gray-coded 2D truth table. The gray code arrangement is not cosmetic. It is the mechanism that makes logical simplification visually obvious. Adjacent cells, horizontally, vertically, and across wraparound edges, differ in exactly one variable. Point 2. Group 1s for SOP, Group 0s for POS. Both follow the same geometric rules, power, of 2 rectangles with wraparound adjacency. The literal conventions are complemented between the 2 forms. Point 3. Always maximize group size. Find all prime implicants, the largest possible valid groups, identify which ones are essential, and select the minimum set that covers all 1 cells. Never settle for a smaller group when a larger valid group exists. Point 4. Don't care entries are free simplification. Treat them as 0 or 1, whichever extends your groups further. Never form a group of only don't cares, and let use don't cares default to 0 in your final SOP expression. Point 5. 5 variable and 6 variable maps are stacked submaps. Cells at the same relative position across the submaps are adjacent. They differ only in the additional variable that indexes the submaps. Cross-submap groupings are valid and often yield the most compact terms. Point 6. Timing hazards are physical, not logical. A logically correct minimal expression can still produce glitches in hardware. If any 2 adjacent 1 cells are not jointly covered by a common loop, a static, one hazard exists for that transition. The fix is a redundant product term. The added term does not change the truth table, only the dynamic behavior. These 6 points will carry you through all the K-map problems you will encounter in this course and beyond. That's all for now. See you then.